Good morning, students.
Good morning, ma'am.
Is it clear, my voice?
Yes, ma'am.
Okay. So we were in micro programmed control unit organization. This is the architecture, simple configuration of microcontrolled microprogrammed control unit. Okay. So here in this block diagram, let us revise the blocks once again. Here we have our control memory. So this is the control memory. So now what the control memory holds?
Control words.
What are control words?
A group of bits that designate a control signal.
Group of
Bits.
Control word is a group of bits that specifies
A control signal.
Control signal or a control variable. Each bit specifies a control variable or a control signal. If that bit is 1, that particular signal is activated. If it is 0, that particular signal is not activated. Okay. So if that particular signal, it's a control signal, if it is activated, what is happening?
That control signal is initiated and
These control signals are connected to the components in your control unit, in your CPU, to perform one particular micro operation, right?
yes,
If you want to transfer contents of PC to AR, you need to activate certain control signals. Those are done by help of control word, which is stored in the control memory. Okay, so these are called micro operations. So these operations are executed with the help of the control signals that are generated because of control word. Okay, so series of control words will be stored in your control memory, right? So what control memory consists of? Control words, not just control words, a group of control words, right? Okay, so for every set of micro operations to be performed, for mainly we aim for execution of a program, which is nothing but set of instructions. Each instruction has to proceed for a phases, fetch, decode, and execution. Every phase requires certain set of control signals. Okay. See, and you know, every instruction has to go by the process of these 3 stages. Fetch is common for every instruction, right? So if I treat what are all the control signals to be generated to perform a specific micro operations related to fetch is the same for every instruction. Am I right? So I can write these set of control words as a subroutine. I can use this as a subroutine so that every time I can call this subroutine whenever I have entered into fetch state. Okay. So likewise, your control memory will be having a group of groups of control words, subroutines indirectly. Okay, so fetch routine is common for every instruction. Similarly, decode. After that, based on the opcode, what is the operation to be performed will be decided, by which it will be known what are the next control signals to be generated. Okay, so initially your control memory will be filled with all groups of control words required for completion of each and every operation specified in your CPU in the form of an instruction. Okay, so every instruction has to go by a procedure of fetch, decode, and execute, whichever are common every time. Okay, so those will be written as a subroutines, right? So you should have a provision in your control circuitry. you should have a provision for not just incrementing for sequencing the control words one by one, but also it should able to jump from or branching from one subroutine to another subroutine. Okay. So here subroutine is nothing but again a group of control words that performs different micro operations based on the specific operation. Okay. So if it is fetch, there are some dedicated set of control words. Similarly for decode, similarly for execution. Execution based on the operation, you will be having different kinds of control signals need to be generated. Am I right? Okay. So all
Yes,
these are called subroutines. You should have a provision here. The control address register should be able to update with many of the possibilities. One is just incrementing its CAR, where it can point to the next micro instruction, which is available in the control memory, or it should have a branch, maybe conditional or unconditional, depending on some of the status bits, or it should know the address of another subroutine. Okay, how can it know? By using mapping process. Okay, or else it itself need to call some other subroutines. Okay, so there are several ways are required for obtaining the next micro instruction address so that it will be loaded into CAR. So first is it can be incremented so that sequential micro instructions which will be available in a particular routine can be executed, or else a branch can happen depending on the status bits. Okay, right? So your control memory is filled with not just a control signals but also few other fields. So out of which one field is status bits, another field is branch address. Sometimes the control word itself will specifies the address where it has to jump. Okay, so it helps to call by itself some other subroutines. Okay, or else it has to get address of the control new subroutine available in the control memory, other subroutine, with the help of mapping logic. Okay, so mapping logic mainly depending on the control, depending on the operational code, which will be there in your instruction. Okay, see if it is add operation, you will be having another set of control words. For subtraction, another set of control words. Likewise, every operation is having set of control words. Okay, so based on the operation, this is the key with which it can go to that particular subroutine. Okay, so by using those operational code bits, the mapping logic helps to get new address to be loaded into CAR. Okay, so these all other parts helps for getting the new address. So here the status bits. So here status bits usually maybe whether accumulator contents are 0 or not 0, or else the most significant bit of the result. Okay, or else any extra bit that was coming out because of addition or subtraction. These are some of the status bits that indicates, that specifies what was happened in the previous operation. Okay, so based on this status bits, the branch logic helps to select either branch address or the continuous address based on CAR, just increment and then store. Okay, so it is a condition. Okay, branch logic will perform certain condition. If the condition is met, it may want to jump directly to this branch address. Nothing but CAR has to be updated with directly the address available in the control word itself. Okay, if the condition is failed, it may not to jump, so that it just increment the CAR and points to reloaded in CAR, so that it sequence will be executed. Okay, if branch happened, it will go to some subroutine, right? Okay, so the subroutine address is available in the branch address. So CAR is updated with the branch address and continue for executing the instructions or micro instructions available in that subroutine. Okay, after execution of the subroutine, it has to go back again to the same location of the control memory as if like a normal program. Okay. So that particular return address it should know. So that return address is held by subroutine register. Okay. This is not the branch address. Am I clear? So subroutine register helps for holding the return address whenever calls or jumps are happened. Okay, so mainly calls are happened. For jump, there won't be any return. Okay, so based on the status bit, okay, branch logic helps to predict whether the condition is met or not. If the condition is met, it has to go to CAR, has to update it with the branch address, and it proceed for generating the control signals to complete the micro operations which were available in the subroutine. Once it completes the subroutine, then you should write a micro operation here in the subroutine in such a way that it has to come back to the place where this jump has happened, this call or branching has happened. Okay, so for that the return address it should know. So before going to the subroutine, the return address is loaded in subroutine register. SPR helps to load the return addresses. Am I clear?
Yes, ma'am.
Okay. So this is what happened in the microcontrol organization. So all these portion is totally related to sequencing, address sequencing. This helps to find out the next address of a control word or micro operation in your control memory. Okay. So in that, next is mapping. How the mapping is happened for finding out the address. Okay. See, this is how the mapping is happening. So your computer instruction, let us suppose, which is of 16-bit width. This is address field, opcode field, and you will be having one more bit called I bit. Okay. So based on the opcode, we'll be having different micro operations. So if here in this example, they have taken 4 bits for your opcode. So 2 power 4, 16 different operations, memory reference operations I can perform, right? So mapping is happened here like this. Okay, so where here 7 bits are taken as an address of CAR. Okay, so in this example, CAR address is taken as 7-bit length. It means your control memory is of size 2 power 7. Okay, so your control memory is having 128 watts. Each location will be having a set of control signals, right? So each location, how many number of bits, that we will see a bit later. Okay, so your control memory size is 2 power 7. Number of address bits required are 7. So your mapping function is like that. It should produce a 7-bit value which specifies the address to be loaded in CAR. Okay, so after decode state, we'll be having your opcode bits. Okay, so based on the opcode, I know what is the next operation to be. I mean, I have to enter into execution state. Based on the opcode, I know what is the next control signals to be generated. Okay, so if it is add operation, you need to activate add function in your ALU. If it is multiplication, you have to activate multiplication operation in your ALU. That particular control signal have to be activated. Okay, so for each operation, so different control signals you have to generate. So I will be writing them as a different subroutines. Okay, so that subroutine address will be available by use with the help of this mapping. So you are now have these opcode bits, and the mapping is happened by adding these 3 bits likewise. Okay. So by which the first micro instruction address of your next operation is like this. Okay. So for a different opcode, let us suppose it is 111. Then this particular operation corresponding subroutine will be at address 0, 1, 1, 1, 0, 0. Am I right?
Yes, ma'am.
Okay. So maybe my next operation, let it be 1, 1, 0, 0. Okay. So that particular subroutine will be at address 1, 1, 0, 0, 0, 0. Okay. So let us consider this address and this address. How many bytes or how many words are gap? How many number of locations are gap in between these two?
1.
1. The 0, 1, 0, 1, 1, 0, 0, right? So next address after this. Zero one zero one one zero zero. This is first starting address of my subroutine. From here, you will be having certain control words that initiate several micro operations to perform, right? Next location will be 0 1 0 1 1 1 1 1 1 0 1, right?
Yes,
0
ma'am.
1 0 1 1 1 0 0 1 0 1 1 1 1. After this 0 1 1 0 0 0 0. Okay, so this is the next address which is dedicated for another subroutine. Am I right?
Yes, ma'am.
Okay. So only the facility is given here for provision of only 4 control words. The mapping is like this. Okay. In this example, each subroutine may have a maximum 4 control signal, 4 micro operations. If it is less than 4, fine. If it is above 4, if your subroutine will take length above 4 micro operations, what should we do? You have to use a
And
space which is free. Okay. So what is the last address with this mapping? Last address is 0 1 1 1 1 0 0 is the last subroutine starting address. Its ending address is 0 1 1 1 1 1 1. So the next empty location is 1 0 0 0 0 0. So from here onwards till the end of the memory, these locations are free. You can use this for defining your subroutine if it is length above 4 micro operations. Am I clear?
yes, ma'am.
So likewise, you'll be having first 64 words related to the subroutines. Okay, because my opcode can start from 4 zeros to 4 ones. If I take 4-bit length opcode in this example. Okay, so first starting subroutine address 0 0 0 0 0 0 0. Ending of that first subroutine is this. Okay, so next subroutine will start from 0 0 0 0 1 0 0. Likewise, till here. Okay, so how many bits? 2 power 6. So first 64 words are mainly dedicated for your subroutines. After that, you can have your own area available for defining your control words. If the subroutine length is above 4, I can use this. How can I use this? I have to write an instruction here in such a way it will jump to that particular memory, control memory address. Okay. Okay. So that can be implemented by using the branch jump operations. Okay. So that will be taken care by your address sequencing. Right. So to facilitate all these things, your control instruction format is divided into several fields. Okay. So this is the micro instruction format. This is the basic instruction format. Okay. So here the 16-bit field is defined in this way. 0 to 10 and 11 bits are here dedicated for your address field. So 11 bits means 2 power 11, 2048 memory locations. This is what your main memory talking about, 2048. Earlier we have discussed about a 12-bit address field. So 4096 locations. Okay, each location is 16-bit width. Here they have taken just 11-bit address field so that you will be having a provision of 4-bit opcode field, 11, 12, 13, 14, 4-bit opcode field, and one I bit. This specifies either direct address or indirect address for memory reference. This is the basic instruction format. When we come for micro instruction format, okay, so which is the definition of each control word in your control memory. So here control memory size is 128. Each location is capable of storing 20 bits. Okay. So earlier, as I mentioned, each initially each control word is having several control variables. Each variable represent one control signal. Okay. So likewise, we have to calculate how many number of control signals or control variables are there for a particular hardware architecture. Okay. So, and we have concluded that we may have hundreds of control signals. So a memory which is having each location that many number of bits is impossible. So we will be doing by grouping together. Okay. So here it is now limited to 20 bits. So these 20 bits are divided into several fields up to 6 fields. Here AD, nothing but address field, 7-bit field. Why this is 7-bit field? Because here this address will gives you address of the next micro instruction available in the control memory. Okay, so 7 bits are sufficient. So 7-bit address field. After that, branch field. This helps whether branching has to perform or not. Okay, and CD. This is the condition for branching which holds the status bits. Okay. After that, we have micro operational fields F1, F2, F3, each of 3 bits. Okay, each field will perform several micro operations based on the value. Okay, based on the bit definitions. 3 bits which have possibly 8 different combinations. So each combination will provide one particular micro operation. So this is how the definition of the fields. For F1, it performs, these are the micro operations. F2, subtraction, logical and transfer. Okay, so this calculates the direct address. This is just transfer of accumulator to data register and incrementing the data register and transferring the contents of PC to DR. Likewise, different micro operations are there for each field. This is F3. Okay. Next, conditional field, or this belongs to actually the status bits. 0, 0 means unconditional branch without any condition. The branch should happen. Okay, what type of branch it is, whether it is permanent jump or else temporary jump. Okay, that will be available in branch field. Okay, so CD field is nothing but status information. U meant for unconditional branch, always no status bits are there here. 0, 1 means indirect address bit. 1, 0 is the sign bit. 1, 1 is the 0 bit, 0 flag indirectly. Okay, so accumulator contents are 0. BR, as I mentioned, it is a branch field. This specifies what type of branch it is. If 0, 0 means it is jump instruction, it is nothing but jump means you are permanently jumping to another control, another subroutine, right? So what may be the case here? For example, once you complete one particular instruction execution, you have to proceed with the next instruction. First micro operation is related to fetch. Okay, so you need to jump to your routine, which is fetch routine. Okay, and it is permanent jump. You don't need to come back to this particular subroutine again. So you don't require return address storage here. So in that case, this type of branch is jump. First instruction execution is completed, then you have to proceed for the second instruction. First phase is fetch, so you need to jump to fetch routine. Okay, for that you don't require any SBR. for storing the written address, right? So jump, it just copies the address field contents into CAR. Okay, address field holds the address of fetch subroutine in your control memory. So CAR will be updated with the address of your fetch subroutine, which is available in your address field in your instruction format itself, right? So CAR is just copied with the address field without any condition. Okay. So if this case, the CD bit should be 1. Okay. If CD bit is not 1, then CAR will be just incremented. So it just proceed for the previous next instruction. Okay. We don't want any branch. It just increment to point to the next micro operation. 0, 1 means call. You want to call a subroutine. See, after, for example, after decoding based on, sorry, you want to call a subroutine. Let us suppose subroutine may be related to, what I can say example here. For example, you want to calculate indirect memory address. Okay, see, in your instruction, you have I bit where it is 1. Okay, and in your instruction, the address field, this address field, 11-bit address field, if I is 1, this is not a direct address. Okay, it is an indirect address. You need to calculate the effective address to perform one memory read operation you have to do, right? Okay, so you every time to calculate the effective address, this particular memory read operation have to be done. AR should be loaded with contents of memory in AR. Okay, that is what a micro operation related for calculating the effective address. M of AR. Okay, so this has to be done every time whenever I bit is 1. If I bit is 1, you need to perform this particular operation to calculate the effective address. Okay. So the micro instruction related to this, whenever I is 1, this particular subroutine can be called every time. Okay. So this can be an example for this field. We are calling this particular subroutine voluntarily whenever we require to calculate some indirect address or anything. Okay. So once you got the effective address in AR, you have to come back to your again same routine and then proceed for the execution. Okay. In that case, your first whatever is the address field available, that will holds the address of this particular memory subroutine, and your CAR will be loaded with that. Once it finishes this routine, it has to come back to again the same location. So SBR should be loaded with written address. Written address is nothing but the next location in your control memory. So SBR is updated with CAR plus 1. Okay. So if the condition is not always, then if the condition field is 0, then I can go by just incrementing CAR. Similarly, written instruction. Once after finishing the subroutine, you have to come back. So you should write a particular micro operation in such a way it can return to your control back location. Okay. So SBR should be loaded back to CAR. This is another branch example. Okay. And finally, map. Based on the opcode field, you will be getting new address. So CAR will be loaded with that particular new address based on the mapping logic. Okay. So how there are 4 ways of loading your CAR here. The 4 ways are nothing but your branch field. Okay. So maybe conditional, unconditional branch, just AD can be copied, or else it can be new address can be getting from mapping logic, or new address can be getting from SBR during written instruction, or new address is available in the control field itself. Okay. And based on the conditional condition, the control field will be updated in CR. These are the 4 possible cases. So branch field is having those many possible cases: jump, call, return, or mapping. So this is an example of micro instruction format. where it uses 128 by 20 as control memory, and main memory is of 2048 words. Okay, and remaining these are common. We have your address register, program counter, data register, ALU, accumulator. These are the other registers and memory available, and this is what you call control unit, which is responsible for generating the control signals. Okay, so that's all about microprogram control organization, address sequencing, and microinstruction part. Any doubts here?
No, ma'am.
Yes, any others? Okay.
Ma'am,
Yes, tell me.
you have to learn the different opcodes for different instructions, ma'am.
This one.
Like this one. Yes, ma'am.
No, not need. It is enough to segregate the fields. Okay.
Yeah,
So
okay,
what are
ma'am.
the micro operation fields? Format is enough. No need of these definitions. But example wise, you can remember one at least.
Yes, ma'am. Even in the previous chapters also, ma'am. Like there were
No
these
need.
kinds of
Those 25 instructions we have, no need of them. But
yeah,
basic
okay, ma'am.
instruction number of instruction formats. We have register reference, IO reference, memory reference. Okay. So
Yes, ma'am.
how those are distinguished, those fields you have to remember. Format of instruction need to be remembered.
Yes, ma'am.
Okay. So detailed all instructions means not required. But every
Yes, ma'am.
what are the type of operations that are performed in each case need to be understand. Okay. So memory
Yes, ma'am.
reference basically they deal with the arithmetical and logical operations, two-word operand instructions. Okay, IO reference means basically it includes IO input read operations, transferring the contents of input register to accumulator, output write operations, accumulator contents onto OPTR, and some other branch operations were also there. Okay. So what are the categories? Globally, you can remember. No need of particular. What is that instruction? Okay.
Yes, ma'am.
Okay. So this unit all talks about a single register organization. Okay. Where you have one and only one register, that is accumulator, mainly for holding one of the operand or the results. Okay. So, but while performing operations, you may require certain values to be stored, like addresses. Okay, we may require to store addresses of some subroutines, or else some counters, or some temporary results during multiplication, partial products, likewise. Okay, so you may require, while the course of operations, you may require to store certain variables or intermediate results. Okay, for that, since it doesn't have any facility, we have to go by memory only. Okay, you need to use memory for storing all these intermediate results or partial products, return addresses everywhere. Okay, so referring memory every time, it is time consuming. Okay, so memory access is basically a time consuming operation. So it is better or more convenient and more efficient way is to store all these temporary values in processor registers itself. Okay, so rather than going with a single processor register, which is accumulator. If I have multiple registers, large number of registers, if they are included in my CPU, so I can easily or most efficiently perform the operations without accessing the memory in between. That will speed up my execution. Okay. So whenever more than one register is there in the system, I require again a architecture where all these multiple registers are connected. Okay. I require again a common bus for connecting multiple registers. Okay. So that is what called general register organization. So as and when you know the definition, the parts of CPU, CPU is having ALU, control unit and registers, not just a single register, multiple registers will be there. Okay. So till now we have discussed about only one register, that is the accumulator. If I have more than one register, how to connect them? Okay. Right. So whenever more than one register is there, I may have communications between the registers to the other parts of your CPU like ALU, right? Or else with the accumulator, sometimes the operations need to be carried out even between the registers, not just with the accumulator itself. Okay. So that is what called general register organization, where more than one register is there. How the, how CPU is designed. Okay. So that deals with your third unit. Anyway, that will be discussed in next class after the mix. So mainly you have to remember what are the advantages or the disadvantages in basic computer organization, which involves only one register. For storing any other temporary values like storing pointers or counters or return addresses or any temporary intermediate results or partial products during multiplication, I have to refer the main memory. Accessing memory is time consuming. So it is better to have multiple registers in the CPU itself. Okay. So that will speed up the instruction execution. Okay. So that is general register organization. Anyway, we'll see next class. So if you want have any doubts related to class test or today's class, you can ask me. So till here is the syllabus for mid one.
Yes, ma'am.
Any doubts you can ask me in the syllabus portion itself or else any topic. Meanwhile, I'll collect the attendance. So till here is your class test one. Anyway, that advantages of GRO is sufficient. Okay. Detailed description will be there in the next class. So we have seen fixed point representation and floating point representation of IEEE standard data representations, both single precision and double precision, and algorithms, addition and subtraction, both sign magnitude and 2's complement. Similarly, multiplication, sign magnitude. Booth's algorithm is for 2's complement. Okay. And division, both restoring and non-restoring. Restoring for sign magnitude, non-restoring is for 2's complement data. Okay. So learn the algorithms with example. Okay. And practice the conversion process, fixed point and floating point conversions from decimal to binary and binary to decimal. Okay, both the cases, single and double precision formats. Okay, and coming to the second unit, instruction codes. What are the instruction codes? What is stored program organization? Okay, and computer instruction formats and the computer instructions, timing and control unit. Okay, common bus system, which is responsible for connecting all the computer registers. Here the computer registers are different. Okay, so like PC, IR, DR, those registers are connected by using common bus system. And the control unit organizations, both hardwired and microprogrammed control units, and their comparisons, the distinction, instruction cycle and interrupt cycle. Okay, so you'll be having two interrupt flags here, like FGO and FGI. What is its significance? And microprogrammed control organization, address sequencing, and the format of finally microinstruction part. So what is the advantage of general register organization over basic computer organization? Okay, so these are the main important topics to be prepared. Okay. I think I'm clear. Can we stop here? Any doubts?
Yes, ma'am.
Okay, you please refer if you have any doubt, refer the video lectures which are available in the portal. Okay, question bank is also available. You can refer them. And assignment 1 is uploaded in the portal. Will be collected after the meet physically. Okay, hard copies will be collected. Right? Thank you. Bye. Bye for today.
Thank you, ma'am.